Okay, welcome back. In the last video, we saw that the state of 2 qubits is a 4-dimensional complex valued vector, suitably normalized. But we asked the question at the end, what if I give you two two-dimensional complex vectors? What is the particular 4-dimensional complex vector that represents the 2 qubits together? So let me write down exactly that question in mathematical notation. So we have qubit 0, let's call it. So we'll give it a little label 0. We'll label all of the coefficients with 0. And so we have alpha 0, alpha 1. Those are the coefficients in the computational basis for qubit 1. And the nice thing about Dirac notation is that we can write this one as 2 new coefficients, but it's the same basis. So these things aren't physical objects, not the same object for qubit 0 as qubit 1. These are just particular vectors with 1s in some entry and 0s in others. Okay, so I have 2 qubits. One is in this state psi 0, one is in the state psi 1. The question is, what is the state that we assign to both of the qubits? And the answer is via the tensor or Kronecker product. And what this thing is a way to multiply vectors together. And how you should think about it is, for every basis element in one vector space, I'm going to multiply it by all of the basis elements in the other. So that's why I'm getting a doubling. So for basis element 0, I'm going to multiply that coefficient by the coefficient of all of the basis elements in the next vector. And then for basis element 1, I'm going to multiply by all of the coefficients in the next vector again. So in matrix notation, we had alpha 0, alpha 1, and beta 0, beta 1. So this is now going to be a 4-dimensional vector, and how you calculate it. So 4, that looks like a good length 4, is alpha 0, alpha 1, and we're going to multiply that by so that looks a bit funky, vector and vector. But that's just showing you that now I have 4-dimensional complex vector that reduces to alpha 0, beta 0, alpha 0, beta 1, alpha 1, beta 0, alpha 1, beta 1. Okay, so all 4 possible combinations of the coefficients of the original vector, or all 4 possible combinations of the basis vectors. Now you'll see a bunch of different kinds of notation that all represent the same thing. So tensor 1. Okay, so that's equivalent in a different kind of notation, where we just don't write down this O times object. And we can also write it like this. So this really means that, and that means that. So this object on the far right is just shorthand notation for the object on the far left. And you might say that this is the most compact, and down here this is the most explicit. So if you're ever confused about, which is there, does the thing on the right actually mean two separate qubits or not, it has to be understood from context. If you already understand that context, then you can write everything out in this compact notation, and that becomes much simpler. But if it's unclear, then you should write everything out in the explicit notation. So as an example, if I have qubit 1 in state computational basis 0, qubit 2 in computational basis 0, then that almost always gets written as the ket 0, 0. Okay. And so this is why we have we call this basis that we wrote last time as the computational basis, because it is just two copies under the tensor product of the qubit computational basis. And I'm sure you can imagine, as we move on with more and more qubits, what's going to happen. There's just going to be more basis elements with bit strings inside of them. Now you might ask, can every vector? So here I have just an arbitrary vector. Let's write it out. Let's use our summation notation since we have that available. Oftentimes what values the indices range over is left implicit, and that's helpful if you don't want to specify how many qubits you have. So we had this arbitrary state here, and you might ask, well, is that always equal to one of these tensor products? So I told you that if I have these two states and I want to look at the complex, I want to look at the state of both of them together, this is how you combine them. And the opposite question is, if I just give you a four-dimensional complex vector, can I always find two states for the qubits so that the original complex vector is this tensor product? And the answer is no. And so we can come up with when you ask a general question and you want to disprove it, all you need to do is come up with a single counterexample. So the counterexample is, now watch the notation, I've chosen a capital psi now. So the state's going to be normalized, and it will be the 0, 0 plus 1, 1 state. So those terms, I did not write it down, but the 0, 1 term and then the 1, 0 term are 0. And this state psi 0, psi 1 has all four terms, but that's okay. Some of them might be 0. But if we look above, you can see that it's alpha 0, beta 0, alpha 0, beta 1, etc., etc. Alpha 0, beta 0, 0, 0, plus alpha 0, beta 1, 0, 1, plus alpha 1, beta 0, 1, 0, plus alpha 1, beta 1, 1, 1. Those two could be equivalent. All we need is the following to be true. That thing should be 1 over root 2, that thing has to be 0, that thing has to be 0, and that thing has to be 1 over root 2. However, note the following. If alpha 0 and beta times beta 0 have to equal 0, then either alpha 0 is 0 or beta 1 is 0. So if that term is 0, one of these two has to be 0. Right. If this is 0, then we have a big problem here. If alpha 0 is 0, then this first term can't be 1 over root 2, because it's alpha 0 times beta 0, so that would have to be 0 as well. Okay, so alpha 0 can't be 0, so it must be this one that's 0. However, if that one's 0, then that over there cannot be 1 over root 2 either. So it's a contradiction. This object here cannot be written this way. It has to be a sum of these terms that have just two state vectors in them. A state that can be written this way is called a product state, because it's just a single tensor product. Okay, so product state, and any state that cannot be written that way. So if some state that is in the space of all states that could be spanned by linear combinations of these these product states cannot be written as just one of the tensor product states, so it's not a product state. It is entangled. And in fact, as we increase the number of qubits, we'll find that almost all states are entangled, and these product states are very special states. Alright, so there we see that we have a little bit more than just combining these individual qubits by just multiplying them, like putting them side by side. Because of the linearity of, well, linear algebra, we can take sums of them and we can't get back to just a single multiplication of two of them together. Alright, so next we're going to see how we can write down the unitaries that act on the four-dimensional state space of the two qubits together. Before that, let me just mention that this implies a conceptually interesting difference between classical bits and quantum bits, which is if I have a classical bit, which I didn't write down in this lecture, but it's just 0, 1, and when I have a second one, that one's 0, 1, and so the two of them together is completely specified by individually the first one and the second one. So if I tell you the first one's 0 and the second one's 0, well, together they both are 0, 0. For a qubit, if I have an arbitrary state, an arbitrary assignment for the two qubits together, that doesn't necessarily imply that I can know both of the states individually. So this is embodied by the phrase, the whole is greater than the sum of its parts. So there's something more interesting going on than just knowing the state of one qubit and knowing the state of the other. That doesn't get us all the possibilities. And an entangled state needs to be thought of as the state assigned to two qubits, which is one object, not two separate objects. So unitaries next.